Okay, it is 10:25, so let's get started. I'm going to close as soon as I adjust the volume here. Okay, this is a little bit better, maybe? Better? Yeah, okay. All right, I'm going to close for the remaining 3 students. Okay, so you've had a while to work on this. This is just a review of what we discussed last time regarding calcium oxide. Nickel oxide has the same structure, NaCl, as that of calcium oxide. And that's what we left off last week, or I'm sorry, last lecture. All right, so let's see. Voila. I see you reviewed the notes, or you've read back 2 slides ago. So good job. And if you are the remaining 5% that did not get it right, we're going to go over very briefly because I do want to go over this question and just reiterate the methodology. Okay. Right, so just like the same way we approach calcium oxide last time with the ionic packing factor, nickel oxide has the same structure, so the atom counting is done in a similar way. So the values that you're given are the ionic radii in nanometers and the atomic mass for nickel and oxygen in grams per mole. So if we count, how many atoms are in each unit cell, that will lead us to the density, which is grams per milliliter or grams per cubic centimeter. Okay, so just to reiterate, atom counting, you should know how to count the number of the cations. There was a clarification question mumbled in the front, and it was whether or not nickel is gray or red. In this case, it doesn't matter, right, because it's a 1-to-1 ratio. And then you should also be able to count the number of oxygen atoms. You can count and just say, oh, well, it's a 1-to-1 ratio. You can know back from calcium oxide example how many atoms there are. Or you can count this way as well. You can count the number of atoms that are at the corner. We've gone over this as to what is the fraction of an atom at the corner. And then at the face as well for face-centered cubic. For BCC, we see that there's a 1 atom in the center, so that's this atom here. This is not BCC, but you can see clearly there's 1 atom that's wholly in the unit cell. And then for each of the edges that you see here, right, the fraction of an atom that is in the unit cell is 1/4 of an atom. So that's how we arrive at atom counting for 4 nickel atoms and 4 oxygen atoms. And you can relate that with the relate the atomic, the lattice parameter with the ionic radii. If you look at the unit cell here, you can see that there are 2R for 1 ion and then another 2R for the other ion. Okay, and so that's how you relate the lattice parameter to the ionic radii, and then you know that the volume of this cubic unit cell is just A cubed. And you can compute, which 95% of you got it right. So I just want to clarify and go over that, okay? Before we move on from ionic packing factor and also density measurement calculations, okay? Yes?
I'm looking at the calculation, and that doesn't make sense because you're multiplying a cube 10 to the 7th times 10 to the 23rd. So how do you get 6.69?
There is a cube that is cut off here.
Because right now I'm doing that in my head.
Where's the 44 coming from?
10 to the 44 Avogadro's number times 10 to the 7th. That's really idiocy. That doesn't change the fact that there's a times 10 to the 44.
Let me see. So atoms cancel out. Oh, this should be flipped. Yeah, so atoms should cancel out with atoms, so this should be inverted. Grams, well, stays. And then moles, if this is inverted, moles cancels out with moles. So there should be a divided. That should cancel out. 7 to the 3rd is 21. Thank you for catching that. So if you do the number of atoms, the units atom has to cancel out with atoms over here in Avogadro's number, so you have to flip that. Yes?
So we still multiply and divide the same numbers, just the...
Yes, the same numbers, but I put Avogadro's number here. It should be the inverse of that, so the units are inverted. Do you see? Atoms. So I put atoms over mole, but it should be... So I multiply instead of divided in the written notation. Obviously, in the computation, I've already done that.
Also, why is the nanometers cube?
Why is it?
Yeah, why is that cube?
It is cube because you have nanometers cube as your unit,
Okay.
and you need to convert it to what's more conventional, which is cubic centimeters. I'm glad I went over that. Thank you for catching that. Okay, so hopefully you had some time to play with Vesta. Yes, no? General nods, general shaking of the head. Okay, there's some thumbs up. Have you had any issues with it? Yes? Okay. Hopefully you find it helpful. It is 6.69 or 6. So if you go back and oh, 6.02 times 10 to the 23rd. There. This value is also given in your book, by the way. There are obviously more digits, but sig figs. Okay, so let's go on to covalent ceramic crystal structures. We've talked about a lot about metallic structures, right? Simple cubic, BCC, FCC, HCP. We've talked about ionic structures. Now we'll talk about covalent structures and review that bonding in these types of systems are directional, right? And so some of the examples that we've already talked about are carbon-based. So here you see the structure of diamond. And you can see that there are, each atom is bonded to 4 nearest neighbors, okay? And this type of bonding in these type of materials can also lead to structures that are less dense than, say, BCC, FCC type metallic bonding. But they are quite applicable in terms of the semiconductor industry. Silicon also has the diamond-based structure. And so understanding this type of structure is very useful in, say, electrical engineering, where you have to think about if this is your structure and you want to increase mobility or carrier charges, things like that, you need to know where the interstitials are going to go and how that affects your overall performance in, say, your integrated circuit or what have you. And of course, when we talk about carbon, there's not only diamond versus graphite, but now there's graphene, and then there's also other interesting structures that are technologically relevant, like carbon nanotubes that you've heard of, C60 or fullerenes or Buckminster fullerenes, buckyballs, all the same thing, right, in terms of the C60 complex. And it goes beyond C60. You can also have a little bit of anisotropy. You can have C70 as well, so it's a little bit more elongated than it is spherical that you see here. But the way these atoms are bonding has implications in terms of the material's properties, right? Carbon nanotubes, the way they're bonding and which direction, whether you have a semiconductor carbon nanotube or a metallic conducting carbon nanotube, that all has to do with how the atoms are arranged. And then, of course, there's graphite, and so you get the electronic conductivity within the plane is obviously very different than in between the planes when it has to go through the van der Waals type bonding. So structure has implication in properties, and a lot of the times in research we refer to that as structure-property relations. Right? We care about what the structure is like for the material because that has everything to do with the property. And the same thing for polymers. We've talked about this as well, how we cross-link, how we polymerize the monomers, how we cross-link polymers so that we have copolymers. That has significant implications in terms of mechanical strength, ductility of polymers as well. And so we will work off of the ethylene molecule quite a lot because it's a simpler type structure than, is a simpler type monomer than, of course, other monomers. And then you can vary the functional groups. You can change the hydrogen to, phenyl groups to what have you, and you can get different applications, right? Just switching this functional group from hydrogen to a phenyl group gives you styrofoam, right? So you can go from a plastic bag to a drinking bottle to food containers. And they have differences in optical properties, mechanical strength, chemical resistance as well, right? So when we talk about structure of polymers, because they're not described in the same way as metallic type bonding and metallic type structures, we often have to give information about, what kind of monomer is it? What mer are you talking about? What's the degree of polymerization or the DOP? And what's the molecular weight overall, right? The degree of polymerization affects the molecular weight, and you need to know that when you're dealing with processing of the polymers. When we talk about polymer structure as well, there's definitely a structure, first of all. You may think, oh, well, it's more amorphous than, say, FCC copper. Yes, but there's still structure. When you do structure measurements, you definitely get peaks that correspond to some type of structure. There might not be as long-range ordering, but there's definitely structure. So that's not to be confused with, so local structure should not be confused with, let's say, the structure that you often think of, which is long-range, Bragg diffraction, long-range periodic atomic structure. So these molecules, once they're formed, they're made up of covalent chains, and they're held together by the secondary bonds that we've talked about. And the short-range ordering can arise in these 4 different ways, where it can be quite linear. So think of, like just a beaded chain. So one monomer just attaches to the next in a linear fashion, and you have these long chains. But these long chains are, they can be coiled up in space. So even though they're long, they can definitely, fold back and forth and zigzag. They can also be branch. So you can have the functional groups that don't always add in a linear fashion. And when you have monomers attaching to each other, of course, some of the examples you've seen, in, say, Gen Chem, where you're talking about alcohols, right? You can have a linear chain alcohol. You can have a butyl type of alcohol where, it's a branch. It's a branch type molecule. So the same way you can have for each of these monomers attaching to each other. And so that's the figure that you see there. You can also have cross-links. So you have these linear chains, and then you initiate a reaction. Let's say you add in sulfur. So that's called vulcanization. And the sulfur that attaches will form sulfur-sulfur bonds or disulfide bonds, and that is responsible for the rubber that is in your life. Right, all the rubber tires have come out from Goodyear, Akron, and that has transformed the way we drive. That's transformed materials in planes as well. So, and there's like a million other examples, right? So everyday household items all come from the invention of cross-linking of polymer chains with sulfur. Hey, that's technologically revolutionary. And then you could also have a network type where there's more sort of a random type bonding that you see here. So there are many ways you can have, you can form a structure for a polymer, and that has differences, that results in differences in, density and strength. And more typically, what happens is you have these types of amorphous structures. They're much more random, because if you have these coils wiggling around, just by entropy, they're more likely to be amorphous. Right? It's harder to pack these, chains together, so they usually don't align very well. But certainly, we do have ways of aligning these chains, and so these polymers are what's called semi-crystalline polymers. So they'll have regions that are amorphous, but they have regions that are crystalline, and we often work on ways to actually control the amount of crystallinity. So you can see here, chains can be amorphous, but they can also, fold back and forth in a regular fashion. So that's a crystalline type of structure in polymers. And since polymers are really everywhere, I've only chosen a few examples, where maybe you wouldn't think of polymers to exist in, but you may already know. So wood is more of a composite of polymers in something. If our definition of what is a polymer, the technical definition is that it's a repeating chain of many mers, right? Poly, many, mer, your unit base. So if that's our definition, but then by definition, DNA is also a polymer. It's a regular chain of repeated units. Granted, there are specific rules about this biological polymer, right? There are certain functional groups that have to bind to other functional groups, and they don't bind with anything else. So there are rules regarding how that polymer gets formed, but it's still a polymer by the technical definition in material science. Cellulose, which is one component of wood, is also a polymer. And you can see here the repeating chain in which you could see all the monomers being bonded together. But wood really is a composite, right? It's not just cellulose. There's lignin, there's like other things in there. But there are naturally made polymers that are out there. And of course, we've taken advantage of that, in terms of making cellulose into other things for our uses. Polyester, right? That's a polymer that you wear. It has wickable applications. It wicks away your sweat, but the pores are breathable enough so that any moisture that gets trapped goes away. So whenever Under Armour tries to sell you these type of technologies, they're basically selling you plastic in a very expensive way. The same thing as Gore-Tex. That's not to say that the price is not justified, right? I mean, this is revolutionary. You don't have to wear cotton anymore, right? I mean, back in the day, one did, let's say. And so, yeah, so you're wearing plastic. And now they've gotten much better about interweaving cotton with plastic so that it doesn't feel so rough on the skin, things like that. So there's also processing that takes place to make other composites that are that are more usable and more user-friendly, say. And Gore-Tex is the same way, right? Anything that can wick away moisture or is waterproof or water-resistant, right? Gore-Tex has figured out a way how to make laminates of all these polymers so that they can sell you a really good jacket for the winter. And then polymers can also make safer batteries. So there's been a lot of work to replace the liquid electrolytes that are in your batteries that transports the lithium ions from one electrode to the other. And so there's a lot of work to develop gel batteries that are polymer-based that can transport lithium ions as quickly in the solid phase as quickly as in the liquid phase. And so there's a lot of progress on that, and there's a lot of commercial successes as well. So when you wear watch batteries or something like that, or even secondary batteries, that means rechargeable batteries, there's a lot of polymers already in that type of technologies that are functional and not just good for storing your takeouts until you get home. And the way you functionalize the polyethylene, even just a simple type of polymer, the way you functionalize these type of materials can result in, you could see differences in density, and you could see differences in the elastic modulus. So for high density polyethylene, that's used for more structural type of applications, and so the figure you see here is that of sewage pipes, things like that, plumbing type of applications. And then if you have these functional groups that are a little bit more dispersed, you get linear low density polyethylene, and you could see you use that in everyday life when you go to the grocery store, when you get a plastic bag, it's linear low density polyethylene. And then when you have a branching that you see here, and you change the functional group to a very particular functional group, which is a carboxylic acid group versus a short alkyl group, and you see some of the monomers here, you get your condiment packets. They can be transparent. They can also be made to be not transparent or opaque. They're used in adhesives as well. So lots of ways to functionalize these polymers so that you get the products for your intended applications. So if you want something that has high toughness, you would make it high density. If you don't care about the toughness, but you're really just looking for, something to store your potatoes, say, or pears, then of course, you just need to short alkyl chains and functionalize it that way. So there's a lot of work done in that. So let me switch over. Okay, so if we're thinking about density of polymers, right, whether or not an amorphous polymer will be crystalline or amorphous, and how that affects density, right? A crystalline polymer will be more dense because you can pack in more of those chains within a unit cell. If it's amorphous, right, it's wiggling about, and you can fit less. Okay, so I hope that clears it up for those who have answered A and C. Okay. Okay. And then when we talk about semi-crystalline materials, we call the crystalline regions lamellae. These they fold back and forth in the structures that you see in red. And then there can also be amorphous regions. That's the wiggly lines that you see in blue. So for the same chemistry, if you're not changing the functional group, a crystalline polymer will be more dense because you can fit more of these monomers within, more of the polymer within a unit cell. And you can calculate that based on the density of the material subtracted by the density of the amorphous regions, and then also normalize that by the difference between the density of the crystalline region and the density of the amorphous region. And so that's the percent crystallinity. So that's just it. It's just a difference between the two, between the crystalline and the amorphous regions, and then multiplied by 100. So typically these values are tabulated, and you just need to know how to calculate the percent crystallinity. Okay. And it's actually really hard to get 100% crystalline polymer material. That's actually extremely challenging from a synthetic point of view, and also from an engineering point of view. Not that people aren't working on it. Yes?
What is rho S? I know rho A and rho C are amorphous and crystalline.
Oh yeah, so that's just the density of your polymer. Yeah, it's S because it's semi-crystalline. Sorry about that. Yeah. Yeah.
Okay, so rho C is density of crystalline, rho A is density of amorphous.
Right. So when I say it's really hard to get 100% crystalline, if your material is 100% crystalline, that will be your density. Do you see? And then the density when it's completely amorphous. So basically what can happen is you can get really close to 100% crystalline and really 100% of amorphous. So that would be the difference.
So if I haven't used that, the density of what's the S again?
The density of your polymer itself. So if your polymer is semi-crystalline, it has some density because it's a mixture of crystalline and amorphous.
For it to be 100%, it would have the density of
The crystalline
itself and the crystallization would be very similar.
Yeah. Right. So basically, you subtract out the density of the amorphous of the polymer when it's amorphous, and that's the percent crystallinity of your semi-crystalline polymer. Yes. You can engineer it that way. You can also try to, heat it up as well. There are ways of doing that. Certainly, yeah, you can have 100% amorphous polymers. Yeah, you can rapidly synthesize something and not control the growth, and so that can also result in very high amorphous density, or a polymer that's much more amorphous than it is crystalline. Okay, I will leave that to you for practice, but that's this figure I like because it captures a lot of the semi-crystalline polymers that are in our world and how it's integrated into what we wear, what we drink out of, what we use for recreational purposes, or also transportation purposes. And of course, there's polymers in the grass that you see. There's polymers in the trees and the forest in the back. So it's really just everywhere. And I like this picture because it has both synthetic as well as naturally occurring polymers. So even though you think polymers, plastic, synthetic, they're also naturally made polymers that we synthetic material scientists try to mimic as well, because nature's already figured it out, right? So we just need to make more of it in a controlled way, which is what engineers do. Okay, so we'll move on to polymorphism. And so the structures that I've talked about before, particularly for carbon, right? You see the different types of structures of carbon, even though it's made of the same element. That's polymorphic, or it has polymorphism, or there are polymorphs of carbon-based structures. So I've talked about carbon. It can occur as a diamond structure, graphite structure, even graphene type structure if you're talking about a monolayer. You can also have different polymorphs for the different elements. I sort of sprinkled it throughout the discussion of chapter 3, right? You can have iron, and there are different names for them, and they correspond to different structures, and they have historic ties to when people discovered these structures, right? So iron can have these phases called alpha, beta, delta, gamma. The list actually goes on and on, but that's all to say, each type of these Greek notations have different types of structures, which of course, once again, has implications to mechanical property. So we can control the chemistry and control the crystal structure to get a particular phase in a material. So titanium, right, also can also have different phases. It's a metal, but it doesn't have as many phases, say, as that of iron, at least that's the ones listed here. So you could have alpha phase, beta phase, and they don't always correspond to the same crystal structure, okay? Not all alphas are FCC or BCC iron, okay? Not all beta phases are HCP, things like that. So when one discusses, these alpha beta notations, it's usually when you're in a room of people that understand the nomenclature or understand because they work in your field. When you say alpha titanium, it means something to you and it means something to them. In this particular case, I don't think it means anything to you, right? Because I haven't told you the crystal structure. So when you're dealing with people that don't work with this in everyday life, you have to define what the crystal structure is, right? So when I say, let's say gamma gamma iron, I have to tell you if it's BCC or FCC, or else it doesn't really mean anything to you unless you've done research in it. But this is just to say they're different polymorphs. So if you just say iron, that really is an insignificant statement, because what do you mean by iron? What crystal structure are you talking about? And what application are we making it for and manipulating it for? Okay. And so we talk about iron a lot because it has historical importance, and it has also current importance, and it has significant uses in the future as well. And it's a common enough material that it's been studied a lot. And it's studied a lot because it's also used in structural applications. The way we add carbon into the interstitial sites of iron affects what application we use it for. And so here's an example that by just heating iron, you can access different phases. You can access the different polymorphs. So before you add in anything else, you can start off with alpha iron, then you heat it up, pass a certain transition temperature. Here it's 912 degrees Celsius. You transform the material from BCC to FCC, and we call that gamma. And then at another temperature, 1394 C, it goes from gamma iron to now delta iron, and it goes back to a BCC type structure. And then beyond 1538 degrees C, it melts, right? At some point, these solid systems do melt. And so you could see that that relates back to density that we've calculated, right? The number of atoms that are in a unit cell are tied to the crystal structure, and thus that changes the density. Okay. Yes. No, this has been uploaded for several days. Are you having difficulty accessing the PDFs? Yeah, no, they've been uploaded for several. You can download it to your notebook. No, actually, I want to get this clarified. Are there issues having access to PDF? Oh, okay. All right. Okay. Right. So, takeaway message: you control the atomic structure by how atoms pack, right? What is the stoichiometry? What's the oxidation state? That affects how atoms pack together, and of course, how they pack together is the crystal structure. And then how those grains pack together gives you your microstructure. So we talk about these beautiful crystalline systems where I say FCC, right? That's based on the assumption that FCC is going to propagate into infinite space, but that's really not the reality. The reality in materials is that you have these grains, and in one grain, your FCC can be oriented in a certain way, and there could be right at the grain boundary, some defects, some vacancy, some twinning. We'll talk about that. And then you have another grain. So this type of system that you see here in this figure is polycrystalline. So you see all these grains. They can match in certain ways, but sometimes there's vacancies, there's voids that you see here. And all of that put together, when you hold something in your hand, or you have powders or what have you, that is the macrostructure. That is the overall structure that you get, and that all gets built from the chemistry all the way up to the microstructure and then the final product. Okay. Okay, and when we talk about structure too, we often tie that with, we talk about the single crystal, right? I've talked about beautiful, perfect FCC, and depending on which direction you're looking at, which direction you're testing your material, right? Your material can experience anisotropy. And all that means is that it varies with the crystallographic direction. Okay, and so if you look at the elastic modulus of, let's say, iron BCC, this is the BCC crystal unit cell that you see here. So if you're measuring in a particular direction, let's say the 111 direction here, that can be quite different than that of the 100 direction. And these numbers I'll go over right after this. But this is just to motivate you as to why we need a formal system to talk about crystallographic directions. Because right now, all I said was, you know, BCC, there's an atom in the center and some atoms on the corner, and that's it, right? But what if you want to isolate those directions and talk about the material in a particular way? And so you can see here that, you know, the aluminum FCC has different elastic modulus in different directions. Same thing with another FCC type material, copper. And then you look at iron and tungsten, and iron BCC is anisotropic, and you can see that from the elastic moduli that are given here. And that has, that you can calculate all of these values based on the compliance matrix components. Yes? Yes. Slide 72. This is just to motivate you and say there are differences in different directions, and also get you started on the formalism that there's a way to talk about this. Interestingly, if you look at tungsten BCC, you can see that it's isotropic in all directions, but the tensor components of your compliance matrix are not. We won't go into any detail regarding that, but if you're part of the 58% that are mechanical engineers, the mechanical engineering majors, you will know what I'm talking about and where you can get those values and where you can derive that. That is a little bit more advanced to tie the two together. We won't compute that, but you should just know that these have origins. The elastic moduli have origins, and you know you can derive this to your heart's content when you deal with tensor matrices. Okay, so that's that. Okay, so back to your question, sir. What are 100, 111? What am I talking about? So we'll talk about lattice positions. How do we get to these atomic sites? How do I communicate with you what are the fractional coordinates that I'm talking about? The direction, also lattice planes. And when we talk about lattice planes, we're talking about Miller indices, all right, the HKLs. And then we'll talk about linear density and planar densities as well, because of course the way atoms packed, that results in differences in overall density, but also the density in the direction that you're looking at, or the plane that you're looking at. Okay, so when we talk about crystal directions, we first have to know how to get the crystal coordinate. So here are just some examples of different crystal directions that have been worked out for you. And the way that one does it just systematically is vector notation, really, right? You look at the end of your vector, you look at the beginning of your vector, you subtract the two, and that is your direction. So that's often called in material science the head-tail method. So if you have colleagues that are in material science at this institution, other institutions, this is the common way of referring to this methodology. And we also like to work in integer numbers. We don't really like fractions. So that's it. The method is just to calculate, you know, the difference between the head, the tail and the head, and then convert to integers. And the way that we write this, right, so is that crystal directions, we use square brackets, and then if they're equivalent, we use this type of bracket notation. When we're talking about crystal planes, we use parentheses, and then when we say, oh, this is the set of all these, the family of a particular plane, we use squiggly brackets. That's all there is, okay? That is the nomenclature. So here are some examples. If you look at this vector that I've outlined in blue over the pink, you can see it starts at 0, 0, 0. O is the origin, or the starting point, most likely. So let's say that example is 0, 0, 0. That's your, that's the tail. And then the head here is, well, where does it, what are the coordinates? So here you just move an X. That's 1. So the box that you see is the unit cell. Okay, unit being 1. So that's 1. And then where is it in Y? 0. And then Z doesn't go anywhere in that direction, so it's also 0. So this direction, if you subtract the two, right, 1 minus 0, 0 minus 0, 0 minus 0, you get 1, 0, 0. And to tell you that that is the direction that I went and not a point, so this is the point, the direction, I say, okay, I've gone along the 100 direction. That's what I mean when I say things like 100, 111, is I just told you where I've navigated in the coordinate system. Yes? Because you haven't gone anywhere. If this is the end of your arrow, right? So you've traversed 1. I'm going to erase just to make this a little bit more clear. Yeah, see, I was going here. So this x goes to 1, and then y, well, you didn't go anywhere. And then z, you also didn't go anywhere. Do you see what I mean? So, okay, a better example, maybe a more complex example, would be something like this example, okay? Where you start at 0, 0, 0, and you go, if this is your unit cell, then this is 1, this is 1 in y, and this is 1 in z, okay? So then that means to get to this point in the crystallographic direction, you've gone half this way in x, and then you've gone half this way in y, and you've gone 1 up. So basically, you're just projecting onto the x, y, z axes for this particular system that happens to be cubic. You can do it to any principal vectors, right? If you have a triclinic system where your angles are not 90 degrees, it's just A, B, C. You have 3 principal vectors. What is the projection onto each of those vectors? So this just goes back to, calculus 1, okay? So if you've gone half in x, half in y, and 1 in z, as I mentioned, you need to convert to integer numbers because we don't operate in fractional numbers for crystallographic directions or for crystallographic planes. So then you just multiply it or divide, however you normalize your set of directions to that of integer numbers. So then if you multiply everything by 2, you get 1, 1, 2. And that is the direction of the arrow that you see there, okay? Is that clear? This one. Oh, that is there. Top left. Oh, yes, so that's just another direction. So let's say, for example, you go here. For this particular example, you've gone. All the numbers have everything to do with the arrows except for the one that you pointed out. There's no answer written already on this. That's for practice. But we can do it together. So 1 in x, 1 in y, 0 in z. All right? Just coordinate system. Very straightforward. Now, let me clear it. Oh, there's a way of. Okay. So I have some examples for us to practice together. So you could be given a direction and you have to figure out what the crystallographic direction is, or you can be given something to draw, right? You should be able to operate both ways. So for you to practice, you should, we can practice one together where you can draw 1, 2, 1. So now if you have to draw it, you just convert it and go backwards, right? Before we had to multiply everything to get to integer numbers. Now go back to fractional coordinates so that you can fit everything into a unit cell. Okay, so if you have 1, 2, 1, well, if you have to convert everything to fraction, you can divide everything by 2, and you get 1/2, 1, 1/2. So when you have to fit that into a unit cell to draw the direction, now you have directions to draw. So you could go 1/2 this way, 1 this way, and then 1/2 this way, and your resulting, let me choose a different color, your resulting arrow will be like so, okay? And we draw starting from the origin because it makes sense and it's easy, okay? The other way you could draw it is you can also choose not to convert to fractional numbers, and you just draw another unit cell, and you go, 1, 2, 1. Same arrow. Now you're just across 2 units. So if you extend this, you should get the same arrow. Okay? 2 different ways of doing it gets you the same arrow. The second option, you have to draw another unit cell. So maybe you don't want to do that. Your choice. Now, when we talk, hold that one question. When we talk about crystal planes, we have a similar methodology. So some of these examples are in your book, but the methodology is the same. You look at where these numbers intercept the principal lattice vectors. So in this case, it's A, B, C, because this unit cell might not necessarily be cubic, right? So it's not X, Y, Z, like a Cartesian coordinate that you might think of. And then you take the inverse of these numbers, and you can reduce the fractions again to integer numbers. So an example that you see here when we're talking about a crystallographic plane like this example, you see that the intercept of this plane along the A direction is right here. So that's listed in your book and worked out for you as 1/2 of the unit cell in the A direction. And then for B, it intercepts at 1, let's say, right, because it's a unit cell. And then in C, you see that it doesn't ever intercept the C axis. And so the notation for that is that it intercepts at infinity. All right, mathematically, that means if you bring two planes and they never intercept, their intersection goes to infinity because they don't ever intercept. But the way I think about it is if it intercepts at infinity, that means the component of the axis is 0 because it doesn't intercept. So 1 over infinity is just 0. That's the other way that I think about it. So then if you look at part 1, where does it intercept? Well, A, it intercepts at 1/2. B, it intercepts at 1. C, it never intercepts. If you take the inverse of that, so 1 over 1/2, 1 over 1, 1 over infinity is 0 to the limit. So then you have 2, 1, 0, and that is your crystallographic plane. And you don't actually have to do number 3 because they're already integers. Okay? And so when you look at a plane like this, if you're asked, what is this plane? What is the Miller indices for this plane? What is the HKL for this plane? This is how you figure it out. Okay? And so the other examples that are listed here, 010, 020, 111, 11 bar 1, so that's -1. I have that example here where you can say, okay, if this is my origin, if I set up my my principal lattice vectors where this is the origin, one can do that. But here you see the intercept is 0, 0, 0, and that's difficult to work with. So what you can do is, clearly the crystallographic plane is not 0, 0, 0, right? So what we can do is you can move your origin and translate the origin so it's an easier system for you to work with. And so let's say if you move your origin to, say, here now of your unit cell, then you could say, well, where does it intercept A, B, and C? You could say, okay, well, it intercepts A right here. That's 1 in A. Intercepts B, also 1. And because this is now 0, 0, 0 as your new origin, you have to go down 1 to intercept. That's where it intercepts with C. So then the crystallographic plane is just 1, 1, and we write bar 1. We don't actually write -1. We write bar 1. Okay, that is the official notation. And I've written out explicitly the remaining parts of this methodology, but you could see there's really no point because inversing it 1 over 1, 1 over 1, 1 over bar -1 just gets you the same 1, 1, bar 1. So if asked what is the crystallographic, what's the Miller index for this crystallographic plane? 1, 1, bar 1. Okay, so, all right, so there's another example for you to practice, but before we go, I just want you to review linear density, that's also in your notes, planar densities in your notes. There are 2 examples for BCC, FCC, and how that gets used in X-ray. Okay? Your homework is due, homework 1 is due Sunday night. Homework 2 has opened, but it won't be due for a while. And also reminder, Martin Luther King Junior Day is Monday, so there will be no classes. Okay?